Now we are going to construct symmetric wave function and antisymmetric wave function from unsymmetrized function. We are going to construct symmetric wave function and antisymmetric wave function from unsymmetrized function. So this is called unsymmetrized function. Generally, HSI equal to ESI is generally is known as unsymmetrized wave function. Okay. Now we are going to construct. Now suppose we consider this system consists of two particles, 1 and 2. I am going to swap. Particles are identical. So H12 equals H21. Hamiltonian will be equal. We are going to consider. Okay. How many energies are there? We have obtained. How many energies are there? Okay, 2 energies. Correct. Of course, both energies are equal. Degeneracy. How many solutions are there? How many solutions are there? 2 solutions. See, this is one solution before interchanging. This will be another solution after interchanging. So 2 solutions are there. For 2 wave functions, we have 2 systems. We have 2 solutions. Suppose if I have 3 wave functions, how many wave function solutions will you expect? If we have 4 different wave functions, how many solutions will you expect? Okay, generally we'll think 4. Generally we'll think 3 for 3 wave functions. Okay, generally we'll think. But actually speaking, for 3 wave functions, the solutions will be 3 factorial. And actually we should say for 2 wave functions, the solution will be 2 factorial. We are going to see now. Okay, whether it is really 3 or 3 factorial, we are going to see. For n number of wave functions, the solutions will be n factorial. We are going to see now. So now our idea is, from unsymmetrized wave function, we are going to construct symmetric wave function and antisymmetric wave functions. Okay, we are going to construct. And of course we know that this is before interchanging and this is after interchanging. Okay, so what was done earlier to get symmetric wave function? We have added these 2. Can you remember? We have added these 2. For antisymmetric wave function, we have subtracted these 2. For not normalized. Correct? We have subtracted. So one is for addition, another one is for subtraction. Okay, we are going to look into for 3 particles. Okay, let us see. So the number of ways in which the indices can be interchanged will give the number of solutions. So indices 1, 2 means that will give you number of solutions of the Schrodinger equation of the system. For a 2 particle system, 2 solutions. The solution of Schrodinger equation for n particle system, it gives n factorial solutions. For 3 particle, the solutions will be 3 factorial. For 4 particle, the solutions will be 4 factorial. This leads to n factorial solutions from one solution. Since n permutations, we are going to look into the next slide. Since n permutations of the n arguments are possible, all these n factorial solutions correspond to the same energy, degeneracy. Thus, all these n factorial solutions correspond to degenerate states. The degeneracy arising due to the interchange is called exchange degeneracy. Okay. And of course, we know about for 2 particle system, which is nothing but symmetric wave function is nothing but just we have added these 2 wave functions, linear combination of before interchanging and after interchanging. Okay, so we know about this. For symmetric wave function, sum of these 2 wave functions, that will be the solution. So we know already about this. So this is obvious. Since interchange of any pair of particle changes any one of the terms in psi s into another one later into former. So we know already. So we have 2 solutions and we have added for symmetric wave function. Okay, the interchange of the particles keeps psi s will be unchanged. Now we are going to have 3 particles. So H psi, which is equal to E psi. So now we are going to have 3 particles, 1, 2, 3, 1, 2, 3. Now we are going to interchange. Okay, what are the permutations will be there? Permutation combinations. There are 6 possible solutions will be there. See here, psi 1, 2, 3, psi 3, 2, 1, psi 2, 3, 1, 1, 3, 2, 2, 1, 3 and psi 3, 1. So there are 6 possible wave functions will exist. Correct? So it means that this is 3 factorial. So now we are going to construct the symmetric wave function and antisymmetric wave function from unsymmetrized wave function. We are going to construct. Earlier we constructed for two wave functions. We have added and we have subtracted for two wave functions. But here small technique is there. Just listen to me. For symmetric wave function, you add all the 6. That will be the solution. Okay? For the symmetric solution, to get symmetric wave function, you just add all the 6 wave functions. You will get the complete solution. So that's all. Very simple one. For the antisymmetric wave function, you will have to go with even number of interchanges minus odd number of interchanges. So that's a rule. How to find out the even number of interchanges? It has to follow certain rules or permutations. For example, the indices, if it follows like this clockwise 1, 2, 3, this is an even number. 2, 3, 1, this is even number of interchanges. Or 3, 1, 2. See, it follows in a clockwise. So this is even number of interchanges. For example, psi 1, 2, 3. You just say here psi 1, 2, 3. Then psi 3, 1, 2. 3, 1, 2. Then just go with psi 2, 3, 1. See? So they are all even number of interchanges. Remaining thing will be odd number of interchanges. You subtract this by this, that will give you antisymmetric wave function. That's all. I repeat, for the symmetric wave function, we have the total number of wave functions. You just add all the wave functions. Okay, for the symmetric wave functions. To get the antisymmetric wave function, even number of interchanges minus odd number of interchanges. How to find out the even number of interchanges? It has to follow the complete cyclic permutations. It has to follow. Okay, so there are 3 numbers exist. Cyclic permutations. Exactly like 1, 2, 3, 2, 3, 1, 3, 1, 2. So they are all even number of interchanges. And this one will be remaining thing. So this minus this will give you antisymmetric wave function. So this is the way that we can construct symmetric and antisymmetric wave function from unsymmetrized wave function. This is the way. So we have added, see, to get symmetric wave functions, we have added all the wave functions. See here, all the solutions we have added. And for the antisymmetric wave function, this will be even number of interchanges minus odd number of interchanges. The sum of these functions is a symmetric wave function, and the antisymmetric wave function, unnormalized wave function, is constructed by adding together all the permutative function resulting from even number of changes from the original solution and subtracting from the sum of all permutative function arising from odd number of changes from original solution. For example, just take 3 particle system. We have added to get symmetric wave function, and for antisymmetric wave function, we have constructed even number of interchanges minus odd number of interchanges. So of course they are not normalized. If they are normalized, the answer will be 1 by root 6. Here also we will have 1 by root 6. Okay, that's all. Is it okay? Now the last section in this unit. So this is about Pauli's exclusion principle. Of course, we have seen earlier Pauli's exclusion principle earlier that we cannot accommodate 2 fermions in the same state. Correct? So now we are going to generalize this one. Suppose we are going to keep 2 electrons in the same state, both should have opposite spin. In terms of quantum numbers, all the 4 quantum numbers cannot have. Suppose if we consider a quantum particle, fermion, or another electron, they should not have all the 4 quantum numbers same. Correct? All the 4 quantum numbers. We will see. We know that psi 1, 2 is a solution of Schrodinger wave equation of identical particles. We know already. Then after interchanging, 1, 2 becomes 2, 1. The electron in the positions with the linear combination we know already. So that we have a solution 2 factorial, 2 solutions are there. We know already this one. For 2 particle system, we are going to interchange. There will be 2 solutions, and this is given by this expression 5.115. So this also will be a solution. Okay. Since the particles are exactly identical, all physically measurable quantities must be independent of exchange of any pair of 2 particles. Hence the probability density, because these particles will overlap. So surely the probability density must be equal. So we know already, we have seen earlier. So now taking the root, that will give you now two solutions. Your A will become plus or minus B. Okay, the solution will become exactly like this. Okay, plus stands for symmetric, minus stands for antisymmetric wave function. Okay. So if you have two particles, your total Hamiltonian will be kinetic energy of the first particle plus potential of the first particle plus kinetic energy of the second particle and potential of the second particle. We know already. In terms of operators, we know this one. And total Hamiltonian will be H1 plus H2, we know already. The Hamiltonian for the system of two particles is the sum of Hamiltonian of the function of individual particles. We assume that identical particles do not interact. So we have assumed. Even if they interact, it is very, very small. Then, in this Hamiltonian function of two particle system, this energy eigenvalue is expressed as the product of wave functions. You have already seen that if there are two wave functions, you will have to multiply. Okay. If there are two wave functions, you will have to multiply to get the total one. You will have to add the energy. Energy should be added, whereas the wave function should be multiplied. So psi 1 comma 2 equals psi 1 and psi 2. So you will have to multiply to get the total wave function. Since the two particles are exactly identical, they are acted upon by the same force, and hence V1 and V2 have the same analytical form, V of 1. Okay, this is potential energy. It indicates that the wave function belongs to the same family. So now, there is no indices like n. We are going to introduce n here, n1. N stands for quantum numbers, all the four quantum numbers. So set of quantum numbers, principal quantum number, orbital quantum number, magnetic quantum number, spin quantum number. So now we are going to introduce with the indices as n1 and this is n2. n1 for the set of quantum numbers for the first particle, n2 stands for set of quantum numbers for the second particle. Okay, the same equation with the quantum numbers we have written, with the same equation, see, with the quantum numbers. Is it okay? This is without quantum numbers, with quantum numbers. Now, this equation describes the state in which the particle 1 is in the state described by the set of quantum numbers n1 and the particle 2 described by set of quantum numbers n2. Now we are going to interchange. We are going to swap the particle 1 and 2. So that becomes psi 1 comma 2 will become plus or minus psi 2 comma 1. Okay, so we can write, generally we can write this equation, okay, like this. That's, we have written now this one. Exactly in this form. We can write with a set of quantum numbers. So now psi n1 of 1, psi n2 of 2, just interchange, that will give you psi n1 of 2, psi n2 of 1. So we can interchange. We can write exactly like this. So this can be written as exactly like this. So put together that will give you psi 1 2, put together that will give you psi 2 1. And of course this equation is exactly equal to this old equation. Okay. So hence equation 5.124 is equivalent to 5.115 when the wave function psi dash 1 comma 2 describes in the state in which one particle in the state n1, another particle in the state n2. So this is with quantum numbers, that one is without quantum numbers, both are equivalent. Okay. Now of course we can construct, plus stands for symmetric, minus stands for antisymmetric. But we are more concerned with the antisymmetric wave function because of Pauli's exclusion principle. Our symmetric wave function, as I said earlier, that all the bosons can be accommodated in the same state. So we don't bother about number of bosons in the same state. 1000 particles, 1000 bosons, 10,000 bosons, we can accommodate. It will become superatom. Whereas here antisymmetric wave function we do not know. So this will violate Pauli's exclusion principle. So now that's why we are more concerned with the antisymmetric wave function. So antisymmetric wave function goes with the minus sign, correct? All Fermi particle will follow this equation. Just take the complex conjugate. Just take the complex conjugate and take the normalization condition. So normalization condition is nothing but which will lead to 1, and of course your normalization constant will become a squared equals 1 by 2. So a equals 1 by root 2 because two particles are there. Correct? Two particles are there. We have formula will be n equals root of 1 square plus 1 square, the same formula. So that will give you 1 by root 2. So your a square will be 1 by 2. So with the normalization condition, that will give you constant as 1 by root 2. Okay, now the wave function is normalized. Suppose if we go for n1 equals n2. So our argument is we can have all the 4 quantum numbers same or not for 2 particles. Our argument. If it goes with n1 equals n2. What will the value here? Suppose we go with n1 equals n2. This minus this will give you answer as 0. But wave function will exist. Wave function should exist. Wave function is there. It cannot be 0. So only thing we can argue that this state is not possible. We can't have this condition. We can't have n1 equals n2. We can't have all the set of quantum numbers for the first particle should not be equal to or will not be equal to n2. All the set of quantum numbers for the second particle. At least spin will vary. Suppose if we have all the 4 quantum numbers, if 3 are equal, at least spin will be different. So one spin will have opposite spin. So spins will be opposite. So n1 cannot be equal to n2. This leads to Pauli's exclusion principle. So this statement cannot be observed. This cannot be equal to 0. Okay. It is concluded that the probability of 2 antisymmetric identical particles is 0. It implies that the 2 non-interacting fermions cannot both be in the same quantum state, and this is Pauli's exclusion principle. Suppose we go for n number of particles. So this is for the 2 particle system. We go for n particle system. Okay, we are going to interchange the same method. So your I h cross d psi by h psi equal to e psi, and 1, 2, 3 r dot n with respect to t, again function of t, that will give you this. Suppose you are going to interchange the particles. So rs becomes sr. See, look at these 2 equations. Your rs becomes sr. So you have interchange now. This resulting solution is also solution of equation 5.129, as it is a symmetry wave function with respect to exchange of identical particles. And surely we will have n factorial solution, as I said earlier, because the n particles exist. So n factorial solution. 2 particles means 2 factorial solution. 3 particles means 3 factorial solution. So n number of particles are there. The solution will be n factorial. So we will have n factorial permutations of n argument of psi. Also, any linear combination of these functions also will be the solution of the wave function below. Suppose we consider that this does not depend on t. So here depends on t. Suppose we consider does not depend on t. Just bring those terms into right hand side or left hand side. You will get this equation. H psi equal to e psi. You bring this e psi this side. H psi minus e psi equal to 0. So H psi minus e psi equal to 0. So H minus e in the bracket psi which is equal to 0. So we can have this. Okay. Now the interaction among the particles. Now this H naught 1, 2, 3 can be written as individual particles. So the individually we can write. So here this term is unperturbed Hamiltonian for the complete system, and this will be unperturbed Hamiltonian for the individual particles. Then the wave function corresponding here Hamiltonian, individual Hamiltonian, the corresponding wave function will be the product of all the wave functions, as I have said already. Okay. What are the energy? The energy will be sum of all the energies. So when you are going to have wave functions, you just multiply. When you are going to the energy, you just add. So that's the rule. Okay. Now you will have to use H eigenvalue equation, H of 1 psi n1 of 1 which is equal to E n1 psi n11. So they will have to obey eigenvalue equation. And for number of n particles, we will have to take the determinant. This determinant is called a slatter determinant. And of course, normalization constant is nothing but 1 by root of n factorial. For two particles, 1 by root 2. Correct? For 3 particles, 1 by root 6. 3 factorial. For n number of particles, we can have 1 by root n factorial. Okay? We will have to use eigenvalue equation and get the solution as determinant. So this determinant is called slatter determinant. The solution is given by eigenvalue equation. Okay. Now we will have to discuss mainly about the Pauli's exclusion principle. Just take 2 by 2 instead of n by 1. Just take 2 by 2 matrix. So this multiplied by this minus, take the determinant of this 2 by 2. This multiplied by this minus this multiplied by this. What is the answer? You will get this answer. Okay. For 2 by 2 matrix, just take 2 electrons or 2 fermions and just swap it, you will get this. Okay, 2 by 2 matrix. So again, if n1 equals n2, what is the answer? This will become 0 again. So which is not possible. Okay, which is not possible. So surely this will violate Pauli's exclusion principle. Wave function will exist, whereas this case is not possible. This cannot be equal to 0. So equation 5.137 suggests that if two wave functions are the same, the state does not exist. The value of determinant is equal to 0. Determinant equal to 0. So they cannot have all the 4 quantum numbers same. Set of quantum numbers should not be equal. So this is known as Pauli's exclusion principle. It says that no two particles described by antisymmetric wave functions are obeying FD statistics can exist in the same quantum state. So we cannot accommodate two fermions in the same state. Thus the antisymmetric state cannot be constructed from a solution which is invariant with respect to the interchange of particles. So this is the conclusion, very important conclusion. So we have seen in this class about fermions and bosons. Okay, the whole universe, the fundamental particles, all are building blocks or particles. Those particles are divided into two categories. One is bosons, another one is fermions. Almost all the matter in the whole universe, everything is divided into two categories, bosons and fermions. So fermions are electrons having half integral spins. Electrons, protons, neutrons, they are all half integral spins. And bosons are boson particles, they will have integral spins like 0, 1, 0, h bar, 2 h bar, 3 h bar, goes on. Whatever the photons are bosons. Phonons are bosons. Electrons are fermions. We are all made up of fermions. So this is made up of fermion. We see the light, okay, photons. So they are all bosons. So I am a boson, you are a boson. We are looking through each other through the force. The force is nothing but bosons. Okay, so bosons and fermions live in the universe. Okay, like us. Okay, thank you students. Bye. That is the end of this whole unit. Okay, in this semester. We will see in the next semester. Bye students.